by Jake Bleacher, not Brent Garry, as stated in the program, for the geology session, and the talk is entitled "The Formation of Pits in Volcanic Environments, Analogs and Lessons for Future Planetary Exploration." Jake.
All right, thank you, and it's a pleasure to be here as we get this transition started from NLSI to survey. And I think if you walk around in the posters and look at some of the other talks today, you'll notice that this pit idea is definitely of interest to the community. So unfortunately, Brent's not here today. We definitely recognize the value of the timing of the survey and the NLSI meetings, but unfortunately it also coincides with field season, and survey did a good job of funding fieldwork this year. So particularly if you're working in Iceland, this is an ideal time to be not here, but in Iceland. So Brent, unfortunately, is in Iceland. So unfortunately, you won't get quite as many food analogs as Brent would normally give you in his presentation, but I will do my best. So we're going to talk a little bit about these pits on the moon, and there's been a good bit of work about it. But I first wanted to note that this is, what we're talking about today is actually a collaborative effort by several different survey teams. So the concept of pits and pit formation is a central question in several teams. Let's see. Here we go. Okay, so brief introduction. Going to talk about pits today. I'm going to present maybe another hypothesis about how they might have formed on the moon, also on Mars, but because of the nature of the meeting, we'll focus on the moon here. Again, this is an effort that's being funded by several field teams. So RISE is funding several of us to look at pit formation in the Plateaus volcanic field in New Mexico. Brent is working through FINESS to look at, in general, lava sheet inflation as a process. David Krang's team is funding some work at the McCarty's flow, where we will be putting together actually a field trip, hopefully to bring people out and become aware of this concept of sheet inflation. And then also some modeling through the DREAM2. Now, the main message I want to get across here, survey by nature is designed to be a collaboration between HEO and survey. So beyond just the science implications of how these pits form and how they might evolve through time is what the influence or impact is on human spaceflight and exploration. So the take-home message I just want to make sure everyone leaves with is that HEO and SMD should be interested in these pits that have been observed by the new high-resolution cameras. If HEO is interested in these, then we really need focused studies on the ground to understand how these things have formed. So regardless of your interpretation of how they formed, I think we probably can all agree on this message right here, which is what I really want you to take home from this talk. So the background, I won't spend a lot of time on this. There are a number of people talking, and you've seen presentations on these in the past. I will point out that this paper came out last week, which caused me to restructure my talk significantly on Sunday. If you haven't read that paper, definitely download and look at it. It's a great paper, gives a good overview, especially of what these things look like, how many there are, where they're located. And unfortunately, it appears I'm talking before either of the authors, so I don't want to steal any of their thunder, but I do need to give a little bit of the background so you can see why we think that inflation might be involved. We've been seeing interpretations that involve both volcanic and or structural influences, but the key point here is that they could be linked to subsurface void space. If they are linked to subsurface void space, then going the whole way back to 1985, Fred Hertz was suggesting that tubes or caves in the surface could be used as radiation protection, and they also provide some amount of thermal stability. So instead of planning for these huge swings in thermal conditions, you can plan to survive in a more stable environment. But I will note that Bill Halliday, who my advisor, Ron Greeley, held in very high respect, he has noted several times that it is difficult, based on morphology alone, to link caves or tubes to pits themselves. And just to pump up Bill a little bit more, Ron pretty much always told me, if you have an idea about tubes and it doesn't fly with Bill, then you're going to have a tough time flying it with me. So This guy is definitely someone he had respect for. Pit morphology, again, I will just kind of cruise through this, but there's a couple things I want to point out here, and this is a figure from that new paper from Wagner and Robinson. Again, please check it out if you're interested in pits at all. But they put together a real nice figure up here that kind of shows some of the key elements, this being the outer funnel on the upper surface. They identify this inner rim, and they also point out layered stratigraphy, and you've seen this in some of the other figures that this team has published. They note that there are overhanging ledges you can see as the vehicle has looked from different viewing angles. And they also noted in this paper, the Wagner and Robinson, that sometimes these pits are associated with locally high topography. They point out that these are located in a number of places, mare, highlands, and especially in the ejecta melt sheets. They're not as common in the mare. That will be what I'm focusing on today. So there's also this high abundance of them, or higher abundance in the ejecta melt sheets. They do note that based on the apparent freshness of these, that they're probably not old features, so they're not active skylights over top of a lava tube, but more representative of collapse more recently into void space. So, again, just to reiterate this point, why is this relevant to survey? The main point here is that remote sensing morphology is often not going to give you enough information to eliminate a number of hypotheses. So the key for me is that if HEO is considering these as a location to use during future human exploration, then we as the science community have a responsibility to make sure that all of the options for formation are on the table. We want to make sure that they know these, and it's critical because some manners of forming pits in volcanic terrains are linked with tubes and caves, others are not. And that is a very key point, and that is why I think all of us would agree that we need to be exploring these things in more detail. In fact, we put these hypotheses on the table. I'm not suggesting, and probably no one else is, that all of them formed in one manner. There may be a number of different processes that have formed different types of pits. But what we want to put on the table today, we call it lava sheet inflation. I'm going to today call it viscous sheet inflation. Here, I'm going to focus on mare pits. Laszlo Kezdi has suggested that inflation is a process that we can see in some of the rill walls, in some of the lava flow textures. Brent had a paper published in 2012 talking about inflation as a possible explanation for some of the Aina D plateaus. But I will point out that there is a paper that has been published suggesting inflation might be a process in lava or in ejecta sheet emplacement. So although I'm focusing on mare, there is at least the consideration that inflation might be a process in ejecta sheets. Okay, so what are we talking about? So I'm a volcanologist. Our team are mostly volcanologists. Most people are very familiar with the concept of lava channels and lava tubes. Endless amounts of reports in the literature. People are not so familiar with the concept of lava sheets. So we'll do a little background on this real quickly. Lava sheets are basically large flat surface areas. They make big tabular flow units. And what you have is basically a crust over a very broad area. So in a sense, a sheet is kind of like a tube in that you have an extensive liquid core underneath a crust on top and crusts on the margin. But one point I do want to make out is that this is pretty much an accepted concept in the basaltic volcanology community here on the Earth. I just have a sampling of papers from the 90s here. This is probably quadrupled in the last decade and a half since these papers, but these are kind of some of the landmark papers on that concept. And if we look at sheets a little bit more in detail here, again, this is a broad advancing flow front that advances as breakouts, toey breakouts, and then it produces a crust on top. So on this picture here, you can see the shiny lava up here is the sheet, and there's liquid in the sheet, and you can see that as it hits the slope break, those toes are breaking out and supplying lava down to the next level where you're now building another sheet. What we're talking about with morphology is basically a balance between the lateral advance of the flow and the flux of liquid into the sheet core. So if you assume that the flux into the liquid core is continuous, as you broaden that flow front, you cannot continue to feed the flow front to advance in all places. So when the advance begins to stall, you form solid rock on that crust, and then it becomes harder for liquid to break through that, and it becomes easier for liquid to push the crust that's riding on the top upwards. This is the concept of inflation. So again, it's this balance between lateral advance and flux into the sheet. Laszlo and Steve Self have noted in the past in several papers that in theory, lava sheet inflation should be much more common on smaller bodies. They were thinking about Mars when they wrote the paper. The moon is even smaller. So again, stalling lateral advance and lower gravity increases the likelihood of sheet inflation. So if you're filling up the mare, you're basically filling a bowl for which you cannot laterally advance past the margin of the bowl, and you have less gravity. So less gravity pulling the lava laterally, less gravity stopping it from going upwards. So this should be a video here, and we'll just run through really quickly this concept. So this is the lava, the active lava. You can see it moving forward, and pay attention. When it stops moving laterally, it begins to inflate. And so here it's inflating, and as soon as you see breakouts on the front, the inflation back here stalls or stops. Now the key thing I want you to notice here is that the lava is basically filling in the low areas. So right here we're surrounding this little high standing piece of lava, pre-flow lava. This is essentially the anchor point for what would become a lava rise inflation pit. So as the rest of this sheet inflates upwards, nothing here to inflate, you end up with a sheet that's a meter or two thick with a pit in the middle where it has not inflated. Let's switch back to the talks here. So that's the video, and we've seen this happening in Hawaii. Ken Han has taken a lot of videos of this. You can find them online. He also has DVDs available. But basically, this is a process that enables centimeters thick lava flows to inflate to meters thick in a matter of days to weeks. And in theory, you can go up to tens of meters, maybe even hundreds of meters over time scales of months and years. Steve Self has applied this to understanding lava sheet inflation within flood lavas, which if you apply this concept instead of open channel thermal models from placing these flood lavas, you actually bring the eruption rates way down, several orders of magnitude, into something that's actually reasonable compared to things we've seen on the Earth in the past. This is a concept that's actually well known to natives in basaltic terrains. If you have walls that you built and the lava flow hits the wall inhibits your lateral advance, inflation occurs. It's seen actually quite commonly in places where we have walls in Hawaii. Okay, here's an example. We'll jump into these now. This is a inflated sheet flow in McCarty's. Again, this is a site that we'll be working with through Dave Kring's survey team. So this is a very long lava flow, over 40 kilometers long, erupted from a small vent right here. Down here to the southeast, it was basically advancing uphill. It was advancing uphill by encountering the slope, stalling the lateral advance, inflating the sheet, then breaking out and filling the moat between the previously inflated sheet and the increasing slope. These are the kind of textures and morphologies that you see, and we'll get a little bit closer in on some of these. So this is an inflated plateau right here, and this is one of the margins. So here you can see Brent is laboring his way up one of these with our differential GPS. And here we see Jim Zimmelman and Larry Crumpler at the base of one of these margins. Okay, so these inflated sheets can actually reach some pretty impressive thicknesses. In this case, it's up to 15 meters, but the base of the sheet is flooded by its own breakout products on both sides. So we're talking about something that's probably pushing 20 meters thick. Another characteristic of this is that you'll have plateaus that are seemingly unconnected and at different topographic levels. So each one of these is inflating based on the flux of liquid into the sheet that it's getting. So often we'll find these hummocky, what appear to be broken down margins or areas between the inflated plateaus, which you see up here. Again, I basically just said that, but you get these seemingly isolated plateaus divided by this hummocky terrain. And within those inflated plateaus is where you find these inflation rise pits. So this is just a more detailed view of that site at the McCarty's. So the pits have quite different morphologies. You can have a gradual drop, or basically a conical form to these things, or you can have an abrupt collapse-like feature and a deep pit like this with an overhanging ledge. Floors are often covered by rubble as you're breaking up that crust. But they can also be swamped or flooded by breakouts as it's happening. So here's just some graphical examples. Again, something inhibits the lateral advance of the lava. In this case, we drew what might be considered a tumulus. Here would be an example of one of those, a pre-flow tumulus. The lava inundates the area but doesn't rise high enough to flood over top of it. As you raise that crust by inflation, you produce overhanging ledges which might collapse or fall in. This is one scenario. Another scenario is that you do essentially the same thing, but then breakouts along the floor of the inflating crust basically swamp or flood that internal terrain, so you can actually produce lava flow textures on the base of the pits. You might also have a scenario where the lava does overtop the obstacle, and when you drive inflation, you bring that roof up with it. So this is a manner in which you can drive that crust up. Younger lava flows could overtop this and produce basically a layered stratigraphy. When that breaks down, it's hard to see here, but you can actually see layered stratigraphy on the inside based on pulses of lava into the inflating sheet. So each pulse basically is divided from the pulse above it by a vesiculated zone. So all pits basically have a sense of collapse. They appear to be collapse-like pits. They can form layering inside of the pit, and they have overhanging ledges, and they can form a funnel-like upper surface that leads down into the pit. The point is that inflation pits are rarely linked to void space. Some real brief examples from Mauna Loa 1859 flow. Here's an inflated sheet. Here's one pit and two pits. We have basically a funnel. Again, it's because of the obstacle. The crust is rising away from the obstacle. It's sagging down, so you end up with a funnel-like structure. You can also have roof between two adjacent pits like that if there was a low area in the pre-flow terrain, but they're not linked by a tube. Here's another example. Again, we have a dual pit right here with kind of a sag roof between it and a cone-like structure above it. If you have an elongate feature that you're flowing over, like a wrinkle ridge or some structure, you can actually create trenches, pits within the trenches, or just isolated pits like this. One last example here is a particularly beautiful one from the 1859 flow. So you've got this one isolated high stand right here. This is the highest inflated plateau within the flow field. You have this one perfectly circular pit right in the middle, and it's just sitting there right in there associated with the topographic high. So in conclusion, inflation rise pits are common on Earth. We see inflated terrains very, very commonly in basaltic terrains, and pits are very common within those. They produce many of the morphologies that were cited in the recent paper: funnels, layered stratigraphy, overhanging ledges. They're found in local topographic highs, but in this case, they're not linked to void space on the interior of the sheet. Now, this is one science interpretation that might or might not represent some or a few of the pits that we see on the Moon and Mars. Take-home message, again from the survey perspective: inflation of viscous sheets should be considered candidates formation mechanism for pits. That's the science part. But what we need to do if we're going to be doing HEO-relevant work here is we need to explore these things in more detail. A number of hypotheses could explain their formation. We need to get on the ground because it's very difficult to distinguish them from remote sensing morphology alone. And we thank Survey for funding efforts to try and figure out some of this stuff. So we will be working on these pits with LIDAR, ground penetrating radar, various techniques like that. Thank you.
Thanks very much, Jake. Yeah. Time for one or two questions. Bill.
I was really intrigued by your statement that you had earlier in your talk about how impact melt, you seem to find more lava tubes than, let's say, in the Mare regions. I can think of some reasons for that, but I wanted to know if you could talk about that, and then are pits more likely in impact melt regions versus Mare regions?
Okay, so that is also part where I'm citing the work of the recent paper. So I don't really want to steal too much of their thunder because I think they've thought about that very well. They do present several mechanisms that could develop them. Now, the point is that papers have suggested that inflation could occur in a lava sheet, in a ejecta sheet. So if you think about it, if you've got ejecta landing and you have head from it driving down slope, you could drive inflation, which could lead to pits. Pits are common if you have basically rough terrain that you're flowing over. So in an ejecta sheet, if you've got blocks on the ground and you're flooding it with this melted viscous lava, it could essentially form pits that way.
We have time for one more question. Yeah, Mark?
Mark Robinson, Arizona State University. I didn't really quite, at the end here, make the connection of why you think that these type of pits are good analog for what we're observing in the Mare. Because the Mare pits are, their depth is about equivalent to their diameter, and we can actually see back underneath an overhang about 25% of the diameter of the pit. And, you know, we believe that we've made a pretty strong case. Of course, I would love to go to the moon and find out for sure that they're very young features relative to the formation of the host material, that is, Mare deposits. So if they are formed in this mechanism, they shouldn't really exist anymore because they'd be obliterated, which is absolutely wonderful geologic term, from macrometeorite bombardment, because in the case of Mare Tranquillitatis pit, the equilibrium diameter is about 200 or 250 meter diameter. So I don't really understand the connection of this formation of pits to the ones we're observing on the moon, in the Mare, perhaps in the impact melt sheets.
Yeah, and that's a very good point, and I really liked in your paper that you made that point, that these are not primary features formed as skylights over tubes. In this case, the third scenario that I showed with basically a sheet overtopping the obstacle and then the crust being inflated above that void space, then if you swamp that by younger lava flows, you essentially get the same scenario that you present in your paper, where you have flows over top of crust over top of an extensive void space, and that collapse comes down and starts to fill in that void. The overhanging ledge aspect, each one of these is different. It's dependent on the surface that it's flowing over. So you can have extensive overhanging ledges that are developed, and the collapse is driven much later afterwards as the rock is weathering and beginning to break down. So may not seem obvious to you, but it does seem obvious to me that the explanations you give fit very well with also an inflating sheet flow. Now again, I think the point is it's difficult to distinguish from the remote sensing alone. So, you know, much like you, I would love to see something go down there and figure that out for us. And that's the question we're trying to deal with Survey, is what do we need to put on the ground to be able to answer those questions. But I'd be happy to talk to you guys about this afterwards.
All right. Thanks again, Jake.